Welcome to a brief video describing the results of FPath Experiment 009. FPath is my project name for experiments on the Feynman Path to nanotechnology. And what is the Feynman Path to nanotechnology? Well, it is the idea that you have large machines make smaller machines, which in turn make smaller machines, and so on, until you reach the point where you can reliably move atoms about at the nanometer scale. Of course, the FPath project is nowhere near that yet. It is now operating at the scale of millimeters. As with experiment 007, this experiment is not a true experiment as such. It is a demonstration of some new features added to the FPath project software tools and a discussion of their utility. I thought you might find a report on this to be interesting. We have all seen these really interesting microimages showing various super small things in epic detail. Such images are many and varied, but the thing they all seem to have in common is a little horizontal bar which provides an indication of the distances involved. In the image on the screen, I've added a red arrow to point to the scale bar I'm talking about. For added coolness, the scale bar always has a bit of text after it indicating if the distance is 50 micrometers or 100 microns or some such. Every time I see one of these images, I get a little bit of calibration envy. Other people have bars right on their images to give the viewer a sense of scale, and I do not have such a thing. Well, until now. This is what I will talk about in this video. How the calibration is done and the other cool things such a feature can provide besides slapping a visual scale bar on the bottom of the video feed. I have now added calibration functionality to the Walnut software. The Walnut Server is the primary control entity in the FPath project. It makes decisions about what should happen and then issues the commands to make it happen. I don't want to talk too much about the internals of the Walnut software. I've posted 3 detailed videos on the subject. A link is in the description, but me giving you a little bit of background now will go a long way towards helping you avoid watching those videos. Walnut software has 2 parts. The software panel you just saw starting is the server side. It runs on a Windows 10 PC. Its role is to accept and process the images from the USB microscope focused on the workpiece. One part of this processing means interpreting the current image state and creating general commands. These commands are then sent for interpretation and execution to the Walnut client software, which runs in Linux on a BeagleBone Black single-board computer. For those of you that aren't familiar with it, the BeagleBone Black is kind of like a Raspberry Pi, but more powerful and a bit more open. Another part of the image processing role is to display the image on the PC screen and, if required, to split the feed in order to record it to disk as an MP4 file. The display portion of this processing is what we will focus on here. Clicking on the Start Capture button displays the video from the USB microscope in a panel on the screen. The processing of the video feed from the USB source to the display, called a video sync, is handled by some free but closed software called Microsoft Windows Media Foundation. WMF is a big topic, so I won't discuss it here, but for those who are interested in that sort of thing, I have written a free 360-page book on how to get started with WMF. A link is in the description. Note the little black bar filled with interesting information positioned across the bottom of the video window. This is called a chyron, and it is overlaid on the bottom of each frame in the video feed by a WMF transform object I wrote and injected inline into the video feed. You'll note that there is no scale bar present in this chyron yet. This is because no calibration has been done. The WMF object that displays the microscoped images is a control called the Enhanced Video Renderer. The EVF's job is to take a stream of video frames and render them as moving images on the screen. For all its sophistication, and it is a beautiful piece of work, it doesn't bother implementing a lot of useful functionality. The major issue relevant to the discussion at hand is that it does not provide a way to hit test the image. In other words, there is no way to get the control to inform the rest of the software when the mouse clicks on the screen. Well, I've been programming since Moses was a baby, and if there's one thing I've learned in my time, is that there is no point in swearing at Microsoft. They have proven to be completely immune to any of the many unkind thoughts I've directed at them over the years. So, what do? You do a workaround, which in this case consists of me creating a transparent panel and anchoring it right over the top of the EVR display. The panel collects the mouse clicks, and it can hit test. This means the Walnut software can know when the mouse is clicked and what the coordinates are. Since the panel and display are locked in place, the coordinates of the click on the panel are the same as the coordinates of the click on the EVR display, and you can proceed from there. I've gone into detail about the hit testing because once you have that, it unlocks a lot of very interesting functionality, including calibration. Let me show you what I mean. Here we see we are on the Actions tab. Let's proceed to the Draw tab. On the screen you can see a standard microscope calibration slide. The longer horizontal lines with the numbers are 1 millimeter intervals, and the internal divisions are 100 microns. If we have a mouse click event, we can do things to the video feed at that location. This is due to the fact that the coordinates of the mouse click on the panel correlate, after a bit of math and trickery, exactly to a pixel on the video frame. We use a tool in this group to draw a line on one of the bars of the calibration slide. Let's draw it here on the large 5 millimeter marker position. The red line appears on every frame. This is why it appears fixed on the display. For those that are interested, the technique here is not to directly modify each frame by reproducing the draw command over and over again. Rather, a second transform is placed in the processing sequence. It keeps a transparent video frame in memory, and the line is actually drawn on that frame one time only. Then some much faster and highly optimized code overlays that frame onto the original image. For those that enjoy a bit of trivia, this sort of thing is called compositing. Anyways, back to the point. The Utils 2 tab has an interesting control. If we use the manual stepper control section here, we can send a 10-step command to the stepper motor controlling the bed containing the calibration slide. We see the calibration slide has moved. If we return to the Draw tab, we can drop a new red line on the new location of the 5 millimeter position we originally marked. Since we have a calibration slide with known distances, we can clearly see that the 10 steps we just issued are equivalent to about 660 microns, or 66 microns per step. Thus, we have effectively calibrated the bed. In the future, we don't need to have the slide in place. No matter what we are looking at, or what the resolution is, all we have to do is mark a point on the video display, hit the bed with a known number of steps, and we can then know the point will have moved a defined number of microns. In this exercise, we have to do the math ourselves. But the computer always knows where the mouse clicks happened. This opens up some interesting possibilities. Let's have a look at the Utils 1 tab. The Walnut software is configured to record the last 2 mouse clicks on the video display, however they may have been caused. You can see the X, Y location of the last 2 clicks here in this panel. Once you have that, it is pretty easy to calculate the distance in pixels between the clicks. Here you can see the horizontal, vertical, and total distance in pixels between the last 2 clicks. Notice, though, that the actual distance in microns fields are blank. If we know that the 2 mouse clicks correlate to a known distance in microns, we can calculate the number of pixels per micron. But at this point, we do not know how many microns represent 1 pixel. We can fix this by moving to the calibration panel. Here, the vertical distance is what we are interested in. We also know that the vertical distance between the last 2 clicks on the video display represents 660 microns. Clicking on the Calc button on the calibration panel uses the data from the last 2 clicks, and it has worked out that the current setup correlates to 0.15455 pixels per micron. Once we know this figure, we can click on the Set button to configure it as the system-wide calibrated pixels per micron value for our current setup. Once the setup is calibrated, the scale bar appears in the chyron at the bottom of the display. Here we can see a visual indication of 400 micrometers. The scale bar is coded to automatically adjust to whatever resolution is currently in use, and this will change to 50, 100, or 200 micrometers as needed. Basically, it uses whatever looks best. If we return to the click distance group, we can see that having a calibration value also activates the distance in micron section. Here we can see that the vertical click distance is 660 microns, which is not surprising since it is the same data the calibration is derived from in the first place. The real value here is that once things are calibrated, besides having a permanent scale bar on the bottom of the image, we can just click on any 2 points in the display and get the distance between them. As long as you do not change the height of the camera to the bed or the focus, the calibration will hold true and you can quickly measure distances just by clicking on 2 points. I will demonstrate this later, but for now, let's try another calibration technique. So, what can you do if you do not have a moving bed with a known number of steps per micron or a nice calibration slide? Let's imagine a situation where you're looking at a work surface and have a completely unknown resolution. Well, what you can do is place an object with a known size on the surface and calibrate off of that. Here is a small sample of nickel chrome wire which is nominally 0.1 of a millimeter, 100 microns theoretically. Measuring it with a good set of calipers indicates it is actually 0.09 of a millimeter, or 90 microns in size. Moving the wire to as vertical a position as possible, I can click on each side with the mouse. I don't need to place red lines here. I could if I wanted to, but the mouse clicks are recorded anyways. If we go over to the Utils 1 tab, we can see the mouse click positions have been updated and the horizontal distance is 28 pixels. As before, we follow the same procedure. The horizontal distance between the clicks is assumed to be close to 90 microns, which is the measured size of the wire. Pressing Calc tells us there are 0.31111 pixels per micron. Pressing the Set button sets the calibration on the system. Once again, we have a scale bar on the image, and future mouse clicks will all be able to calculate a distance in microns between them. So let's put that calibration to use. Let's have a look at something interesting, like a bee leg in some random orientation. If we click on one position, here at the bottom of its toe, and again here at the top of the ankle, we can see over here in the distance in microns group that the length of the claw of a British black bee is 238 microns. Well, that could be useful to know if it ever comes up in a pub quiz. So, in summary, that's how the calibration works in the FPath Project software. Note that all of this calibration functionality actually stems from the ability of the software to detect the position of the mouse clicks on the frames of the video feed. Once you have that, you can easily work out a lot of really cool stuff. Oh yeah, as a bonus, if you can receive mouse click events, you can also get the color of the pixel under the last click. Have a look down here in the RGBA group. You can see that the color of the last pixel clicked on is 24:15:2 with an alpha intensity also of 2. Not too useful for bee legs, I'll admit, but in general, this is the sort of utility you really appreciate if you're implementing image recognition algorithms which trigger on colors. Otherwise, you're continually pasting screenshots into some image processing software to figure out what color ranges you are dealing with. Well, that's all for now. I just thought you might be interested in how the newly added calibration features work in the FPath project. Thanks for watching, and see you next time.